So, hello everyone. My name is Krishnakant, as you all know. So, the main thing is for the topic that I have started is that I want to explore some, you know, I can say various fields. And nowadays, the main field can be its quantum mechanics, for which we have to go and learn something called its basics. So, I choose to start with linear algebra. Linear algebra. So in this talk, I will talk about some basics of linear algebra and its applications with quantum mechanics and how we can implement this linear algebra properties and vector spaces, Hilbert spaces, and so further on, we will talk on this. So we will talk about some inner product spaces, Hilbert spaces, eigenvalues, eigenvectors, and its applications in quantum mechanics. So what is a vector space? Vector spaces can be, I can say that vector spaces consist of set of vectors, and vectors are somewhat, I can say, arrow-like structure that you can see here. This U in the vertical axis and this V in the horizontal axis. And this can be known as, this can be said as vector space. This can be said as vectors, and the combination, or I can say, uh, the representation of both, or I can say,
This will go on, go on. You basically mean a collection of vectors, yes?
yes.
If you have many vectors and you have collection. Go on.
So think of a vector space as a playground where you can do two things. Okay. So you can add vectors together, like putting them into end to end, and you can stretch or shrink them by multiplying by a number or by a scalar. The playground follows. Um, so what I am trying to explain this by doing the adding the vectors and putting them into end to end and multiplying by a scalar or a number can be can help us to understand and solve problems in many areas. So uh, we are talking about the quantum mechanics. So we will talk about this in the aspect of quantum mechanics. So there are some properties of vector spaces, such as here is commutativity, which means you can add two vectors uh, by changing the order, such like this. Uh, and think, uh, consider a vector u and a vector v. So the product, added. So when we do the sum of these, which this will be equal to the sum of both the vectors if we change the order, such as that this is u plus v, and it will go on after the it will show the commutative property, and it will go v plus u. For suggest think that this these u and v will be the part of v, or will belongs to the vector space v. We will consider the vector space v in this. The next one property is associativity. Okay. Consider three vectors, which is u, v, and w. So what we can do here is u plus v. First we will do the sum of u plus v. Then the third vector w will be taken, and here we can write it as u plus and the conjugate sum of v plus w. Now the next one property is additivity, and in this property, uh, assume that uh, zero is a vector which belongs to v vector, which is I can say vector space v. Okay, and there will be the additive identity follows, and v plus zero will be the exact vector which we have taken in the starting, and same here is multiplicative identity. What we do is multiply the vector space by any scalar will also belongs to the vector space v, which we can say. So what is the common what's the common thing is here is when we perform any action or any I can say that commutativity, we can add them in any order or any multiply by them in a scalar will belongs to the original vector space which we have considered earlier. Now we will move on to the next section, which is inner vector spaces. So what I can say, what is inner vector spaces? For understanding the inner product spaces, we have to learn what's the inner product is. So we have learned that the inner products are of two types, scalar product and vector product, which I can say are termed as dot products and dot products and cross products. So an inner product on a vector space V, consider a vector space V over a field F, which is usually the field of real numbers or complex. So here the field F is a maybe in the combination of real numbers, or maybe in the maybe it can be a complex number, or maybe it can be a real number. So we will define the function vector space V as V cross V. Here the V cross V is the inner product space, inner product here, and this F that satisfies the following properties, such that if we consider U, V, and W three vectors which belongs to the vector space V, and all the scalars we consider them as alpha will will also belongs to the field F. Now we will talk about some properties of inner products. So generally we consider a U and V vector. So what conjugate symmetry is, we can say I can say that you if we perform any action between U and V, it will be it will be a conjugate symmetry of its own, just like this. If you take if you perform action between U and V, and it will be same it will be the conjugate symmetry of V and U. So where I can say this part V and U and is the complex conjugate, which means it will consist of the complex function iota, complex complex iota for real vector spaces. For real vector spaces, what will happen here? The bar, you can say that's outline, or you can say the above line will be okay. Now we will talk about some properties of inner vector spaces. So the first we will talk about the norm property, and what so we will talk about the properties of inner product from the Pythagoras theorem, which will be the third one. So consider any vectors u and v, which then if we do perform any action between them, u and v, as relation with the Pythagoras theorem. So u plus, you can see here, u vector plus v vector ka whole square will be the u square plus v square. Now we will talk about the triangle inequality. As you know, ki sum of two sides is always greater than or equals to the third side. So same case will be applied here with the inner products. So u plus v, consider u vector and v vector. The summation of will be will be will be the great will be greater than the summation if we take them separately. So now we will talk about the Hilbert spaces. So what's the Hilbert space? Is it a Hilbert space is an inner product inner product space that is complete within the aspect of norms, or I can say normal, induced by the inner product. So formally, a vector space, consider a vector space H with an inner product dot and dot. We can say perform same action with the same vector. This will be called the Hilbert space. So we will talk the examples of Hilbert spaces. The 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 the
That's Euclidean space. Okay. Euclidean space Rn, it's in real space. Go on.
So Hilbert space is an inner product space that is complete